graphing calculator program has a nice feature in that if you put in like your limits for your domain, it'll actually draw your domain for you. So if x goes from -1 to 1 and y goes from 1 to 2, this is how your domain would look like. So that looks interesting. If you haven't already figured it out, if your limits are constants for both the inside and the outer integral, then you have a rectangle. In case you haven't figured it out. Okay? If your limits are not constant somewhere inside, then you're not going to have a rectangle. So the second problem on your quiz looks like this. The region should look like this. Your y limits went from negative, or went from x squared to 4, and your x limits went from 0 to 2. So this is how your graph should look like. And so if you were to draw a line, if you, instead of integrating with respect to y first, you decide you want to integrate with respect to x first, then your x value should go from 0 to the square root of y, and then your y value should go from 0 to 4. And that'll give you the same graph. Okay? So yesterday we did stuff in polar coordinates. One of the limits that we came up with in polar coordinates was this circle. R is equal to 2. And then another circle, R is equal to cosine theta, or 2 cosine theta. And we wanted the part of this in the first quadrant. So our theta went from 0 to pi over 2. And if you were confused as to what part of the circle that took up, we set up our integral with r going from 2 cosine theta to 2, and then our theta went from 0 to pi over 2. So if we graph this, this is the piece of the graph that we would be looking at. Okay? All right, I was playing around with more of this graphing calculator business, and to visualize some of the other graphs that we had using graphing calculator was kind of tricky. Here's the intersection of two cylinders. So if you can see the intersection from here, that's great, but what we probably need to do is we need to trim this down a little bit so you can get a closer view of what's really happening. And so another thing that we're going to end up doing is we're going to, you know how we parameterize curves in 2 dimensions and 3 dimensions? We have one parameter t. So later on we're going to get introduced to having 2 parameters. We can use t and s, or we can use u and v. We can even use r and theta and a variety of different ways to parameterize. And so when you parameterize with 2 parameters, it won't be a one-dimensional figure anymore. It would actually be a 2-dimensional figure, and it turns out that surfaces are 2-dimensional figures. So let me show you this parameterization. So we wanted to integrate to find the intersection between these 2 cylinders. We wanted to integrate over a circle. So this is essentially our domain, and this is where we said we could do this in Cartesian coordinates, and then we eventually change this to polar coordinates. But this is what we're integrating over. And so if we take a look at one of the surfaces that is restricted to just this domain, this is the top part of that cylinder that's laying sideways. The cylinder that's laying sideways is this one, right? So the top part of that is this, when we're restricted to just that domain, and then we can attach the bottom part to that. And so if we want to cover the sides, we can just put that cylinder back, but if we put that cylinder back, it's going to cover the whole thing. So if we want to actually get a visual of this, we need to restrict our z values going up and down. And so for that, I also parameterize this. So this is the volume that we're actually looking for. Okay? All right, so last time, Jesus wanted to see this visually, and I tried to do this, and it was kind of weird and confusing looking, and so I spent a little bit of time trying to figure out how this thing might eventually look like. And so let's see if we can get a better visual of this. So this is the story here. We have the surface, z is equal to x squared times y, and then our cylinder, x squared plus y squared is equal to 25. So that's essentially going to be our domain. That's our D. We're going to integrate over that. And so what I did was, what did I do? I don't know what I did. Oh, so I basically took that cylinder, or took this surface. Let me take the cylinder out. I basically took the surface and I redrew the surface only restricted to the cylinder, only restricted to that circle. So that's the surface. You'll see it's not even the circle, it's only half a circle, right? Now that I'm looking at it, yeah, it was just half the circle. So this is how it would look like, half of that circle. So if you imagine a cylinder going down, then that would cover it. So if you actually want to see the cover, well, I can put the cover on. This is the bottom of it. And these are the sides. So now it's filled in. So that's your volume. Okay? So doing this, if you're looking at these equations that I'm putting up here, these are parameterized surfaces. These are, like I said, things that hopefully you'll eventually be able to do, or at least the simpler ones, like being able to recreate the parabola or paraboloid and a bunch of other surfaces that are really common. So trying to recreate a surface that looks like this might be a little bit more difficult. But I want to show you how it would look like if you don't have this program. The 3D calculator plotter has a nice feature for this too. Lisa? The whole file or just the picture? Okay, yeah. You might have to send me an email because I'm probably going to forget. But anyways, the 3D calc plotter has a, has a nice feature. So, for example, the graph that we were looking at yesterday was x squared times y. And it looks like this. And we wanted to have that the domain to just be restricted to the half of the circle, right? And so if you look at an option here under graph, add a region. So you can describe your region by the top half of the function and the bottom half of the function, and then which function are you trying to restrict. So if we take a look at 0 and the square root of 25 minus x squared, from minus 5 to 5. Then we see this is supposed to be a semicircle, but it's kind of drawing it to scale. So we see this, and then, boy, your graph kind of got weird already, huh? Zoom out. We see that, I guess it's hard to see. Kind of like that same picture. And if you need to adjust the axes, like we want to go from negative 5 to 5 in our x, minus 5 to 5 in our y, and in our z, it goes from 0 to, I think the height of this, if I remember correctly, it's about 15 or so. And I guess let's scale this to have a 0.25. So we'll squish down the z-axis a little bit. So this is the graph that we were just looking at a little bit earlier. Except you can do it in 3D plotter, and I think you could do it in 3D plotter a little bit easier. In fact, that region that I was talking about, I'm going to say add a region. You can graph the region in polar coordinates as well by letting your r, your top function of r, bottom function of r is usually 0, unless you know how it changed last time. And then the top function of r is well, the top function, the outer part. So you can try to visualize what it is you're doing in your web assignment and homework stuff, and then you can use this. It's a free program, it's online, so you can just run this and take a look at the graph to give yourself some visual satisfaction when you're doing your homework. Yes? Probably, yeah. All right, so let's see. You guys have any questions? I had a lot of questions about homework right before class is starting. Yeah? (15.4)? 15.3, number 6. So I'll try to do this by hand so that you can try to get used to being able to do these problems without a graphing program. But after that, let's graph it so that we can be visually satisfied. So we have under the plane and above the region bounded by this two-dimensional thing. So the plane is going to be this is going to contribute our three-dimensional picture, but without a grapher, this is really what we need to focus on. So let's see how this thing looks like, and you need to be able to know what this thing looks like without a graphing calculator or anything. So x plus y is equal to 1 is a line, right? And if you figure out the slope and the y-intercept or whatever else you need to do, this is going to be a line that hits the x and the y-axis at 1. Okay? Now this might not look like a type of function that you know, but if you solve for one of the variables for a lot of these things, you'll see that, oh yeah, that's just a parabola that's negative x squared, so that's turned upside down and that's moved up 1 unit. So this is a parabola that looks like this, and if you find out what the x-intercepts are, it's positive and negative 1. So for the second one, y is equal to 1 minus x squared. Oh, that's still black. You'll have a parabola that goes down like this. So you, between these two functions, there's all kinds of areas that you'd probably be dying to shade, but there's only one correct one. And again, it's like those regions that you rotate about an axis back in Calc 2. You have to figure out what region to shade before you rotate it, right? So that's the same idea. You have to figure out what region to shade. So now if you transfer this in 3 dimensions, again, trying to do this without a grapher, I have this region in 2 dimensions that look like this. This is flat on the xy plane. And then you have this plane, z is equal to, or if you want to find some intercepts maybe, when x and y are equal to 0, z is equal to 3. When y and z are equal to 0, then x is also equal to 3. And when x and z is equal to 0, it looks like it's negative. Y is equal to negative 3/2. So the hard part to try to visualize is imagine that this is going to go further out this way, some plane, and then what you're going to come up with is a slice that looks like this, some volume. Okay? All right. So you could do this problem without visualizing this. This is really all you need. So given that we know this information, let's set up our integral to find that volume. So this is going to be our surface that's above the xy plane, so we would want to solve for z here. So this is our plane. Z is equal to 3 minus x plus 2y if we solve for z up there, and that's going to be our integrand. And it depends on how you want to integrate with respect to which variable you want to integrate with respect to first. Let's figure out which one do you guys want to do first. In this case, it doesn't matter. Any ideas? I think y is already solved for. I'd maybe solve for y first. Y and x. Draw a line parallel to the y-axis. I hit this line. Y is equal to what? 1 minus x. So 1 minus x is my lower bound. I'm going to be inside of the region, and then I'm going to get out my region when I hit this. Y equals to what function? 1 minus x squared. And then the constant limits for your outer limits go from 0 to 1. So that's your set of limits. Your integrand is 3 minus x plus 2y. You decided that you wanted to integrate with respect to y first, and the limits are from 1 minus x to 1 minus x squared. And then your x goes from 0 to 1. Punch it into Wolfram alpha and then put in the answer. Okay? Well, I don't know. I mean, I have my integral thing that I can punch in here. because I have Mathematica, but if you're using Wolfram Alpha, sure you can. I'm just wasting time now. So integrate double integral. The integrand was 3 minus x plus 2y, and I want to integrate this with respect to y from 1 minus x to, maybe I can y from 1 minus x to 1 minus x squared. So close that first integral, and then now I'm integrating that. After I integrate with respect to y, I'll integrate with respect to x from 0 to 1, and we'll see what happens. That's pretty tight, huh? So the command too, I bet, yeah. Does that mean you guys are actually going to look at the notes? All right, that's your answer. Should we check if it's right? 37 over 60. Okay, looks good. Let's move on. Is there anything else that we should talk about double integrals before we move on? Yeah? What happens if they don't have limits? For double integrals, no, you're always going to have limits for these things. So the single integral, no limit business, the indefinite integral just applies to single integrals, and when we take the antiderivative of like a vector function, then we have those C constants. But for double integrals, we'll never do that. We always have limits. This is a computation of something that we're trying to find the volume, or some other application like mass, like what we're going to talk about today. Okay, so no indefinite integrals for double or triple or path integrals, line integrals, surface integrals, flux. Those are the other integrals that we're going to get to know intimately well. Yes, I did say flux. All right. Mass density. I think I have a I thought I had a lecture prepared. Okay. So, what's mass? Amount of stuff. So we've seen equations of stuff Right? Mass equals density times, I don't know, we studied length. Density times length was a popular one that you guys studied in Calc 2. And density times area, and density times volume. So it depends on the scenario that you're given. An example would be the density of the rod. If you have a rod that's it's a little bit more dense on one side than the other, then you have a variable density here. So if you want to find the total mass, you would integrate from point A to point B of this thing. Now, in Calc 2, density times area, it depends on what the area is. A lot of times you're dealing with some sort of linear rectangular area or something where you just, the density changes as you go along an axis. And then maybe they even got fancy one time where they changed the density with respect to the radial distance of your whatever it is you're trying to take a look at. So in that case, that's assuming that the density around one radial distance is different from the density around a different radial distance, but it's the same if you're walking along that circle. So this is, again, a one-dimensional treatment of density. And for volume, well, we could take a look at a volume, but maybe the density changes with respect to a variable like height. So a cup of hot chocolate is more dense in the bottom and lighter on top. And so to actually figure out the mass of your hot chocolate, you can, if you can describe the density of your hot chocolate with respect to this function of the height, then again, it's a one variable function. Okay? So those types of densities you've already done, I hope, in Calc 2. So whether you remember them or not, or whether you did well on them or not, you've seen them before, and they're all just densities with respect to one variable. So now, naturally, we could talk about the density with respect to two variables. And for this, we can try to get fancy and go area and volume, but it's really just better to focus on volume. So they have what's called a lamina. That's what they call it. What's a lamina? Lamina. It's like a sheet of something, right? Lamina. It's a sheet of something. Yes. So when we describe a sheet of something, then we're looking at something that's two-dimensional. So whatever the shape of that two-dimensional thing could be your region. And what we're saying is that now in double integral language, or as a function of two variables, we could take a look at the density function as a function of two variables. Now, we're not just restricted to, we're just going to move along a directed line segment, an axis, and instead of having a constant density, or the density changes with respect to one of these things, or density changes with respect to some circular region, we can actually describe the density by just seeing how dense it is at any point on this thing. So in other words, if I'm over here, I can say this is denser than this point, and it doesn't have to be with respect to one variable. It's going to be with respect to your x and y position. So they'll have different densities, and your densities will be dependent on your x and y position. Okay? Yeah. Delta. Yeah. Yeah. Sigma. Density starts with a D. So I'll call it whatever I want. No, I've seen it called rho, and I've seen it called delta. And so actually I've never seen it called sigma.
I thought area was sigma and then rho was volume density.
I don't know.
Density.
Maybe. So, yeah, Misa. We're kind of, what we're doing is we're adding up a bunch of these densities to find the mass. So the mass is equal to the density times the area.
I'm sorry, if you're doing volume, right? So this is just the domain of the three-dimensional.
No. This is a flat two-dimensional lamina. This sheet, it's a flat sheet, and at some point on the sheet, it's thicker than another point on the sheet.
What's your variable?
So the variable is going to be x and y. Oh, what happened? So your density has, instead of just having one variable like you've done in the past, like a variable like x here, or like x here, or like r here, or like h here, instead of just having one variable like we've had in the past, now you have the flexibility to have two variables. And your density will change with respect to wherever you are on your sheet. And then if we just if we take the area of the sheet, and if the density was uniform all the way across, then the mass is just going to be the constant density times the area, and you're done. But if the density changes with respect to x and y, depending on where you are, then what we could do is we can break this up into little pieces and then take little densities of each little square and find the mass of the square and then add them all up. And then you'll have a better approximation. And you know that when you add up a whole bunch of things with a certain process to it, then it's the Riemann sum that becomes an integral. And this time we're integrating, we're adding up sums along the x and along the y, and so then that becomes a double integral. Yeah? I'm not sure. I'll say yes. So let's take a look at maybe a simple density problem before we get too carried away with stuff. We have to talk about center of mass also, but let's talk about the density first. Oh, I was going to do something first. What? Well, let's do the mass, and then we'll do center of mass, and then we'll see if hopefully we'll have time to do that last bit that I wanted to do. This is the next section, 15, 6, 5. 4 is the polar coordinates? Okay, so this is 15.5. Let's do the red one. So my lamina, my sheet, looks like it's on the, oh, they do use row here for, okay, let's use row. 0, 0, 2, 1, 2, 1, and 0, 3. Hey, I was just looking at this problem, huh? So this is my sheet. And my density is this density function x plus y. So my density maybe at this corner point over here is 3, 2 plus 1. My density somewhere over here would be whatever. You just add x and y. So, and then if this is density in grams per square meters or grams per or kilograms per whatever, whatever the units. I don't like messing with units too much. You could do that in physics. So here we have this thing, and so really all you have to do to find the mass is going to integrate the density function over your domain once you have your domain figured out. Really, that's all you need to do. So we figure out our mass by setting up our double integral. And again, you should try to figure out what you want to take the integral with respect to first. So what should we do first? X or y? If you do y first, you would draw a line parallel to the y-axis, right? Oh, you guys are shaking your head. No. Okay, we want to do x first. Why? Why? X. X. Y first. No, x first. Why? Okay, so if we were to do this integral with respect to y first, one cut for y would give me one entry point and one exit point. If I make my cut along here and eventually make my cut over here on this side, I'm going to enter through this same point, but I'm going to exit through a different function. So I don't want to do that because that's going to require me to do two different integrals. Two different double integrals. So I don't want to integrate this with respect to y first. Let's integrate this with respect to x first. And if I draw a line parallel to the x-axis, I'll see that regardless of where I am along my y, if I draw a line parallel to the x-axis, I'm always going to be entering the same x function and exiting the same x function. So I want to integrate with respect to x first. All right, this line is a line that goes through the origin and has slope maybe rise over run, rise 1, 2, so 1/2. So that's just 1/2 x. Y is equal to 1/2 x. But I want to get x by itself, right? So y, x is equal to 2y. So that's my lower limit. Jason? Oh. Okay, my other one goes through here. If I can figure out where my x-intercept is, that would be easy. Otherwise, I'd have to do the slope thing. Can you guys just tell me what it is? What's this equation? So, one. Yeah? That works. You can tilt your head sideways and look at it from the other side of the board, and then It's like the point slope formula, sideways. Or you can find a slope and come up with the equation of your line. You have to imagine you're looking at it from this side.
No, because when we move the x,
Right? It's like now the x-axis is going up. Yep. Did I draw my region wrong? Yeah, I drew my region wrong. All right. Can I just make it 3-0? Thank you. Okay.
oh well.
Sorry, I drew my thanks for that. All right, anyways, this is my new problem. I'm on my way to the correct solution now. So my x is y plus 3, right? So that's my upper limit. How about my y goes from what to what? Always constants, right? Always, always, always. Well, you guys want to make your own question on the test? I'll think about that. I don't know. That might be. All right. So my rho is x plus y, and we decided we're going to integrate with respect to x first. The lower limit is 2y. The upper limit is y plus 3. After we made the correction, and our y limits go from 0 to 1. And so this is our double integral, which is easy enough to do. Okay? Yeah. Say it again. Uh-huh. Is that right?
I tried something new.
If you plug in the 1 for the y, you're going to get 4, and you will get 2, 1.
3 minus x? Okay. So that means I want x by itself. X is 3 minus y, right? Okay. Minus y. Yeah, so when I was making that video, it has to be absolutely perfect, right? I have to check and double check my work. Like when I'm just lecturing like this, you guys just correct me all the time. Because I make mistakes on purpose so that you can just want to make sure that you're paying attention. Cool. I'll be paying attention for the test. All right. Let's put the center of mass on hold for a little bit, and I want to change gears and go back and do a problem that I find really, really interesting. Yeah, so do you remember this in Calc 2, and then your teacher just said, oh yeah, we can't do this. Okay. So we can't really do it. But in statistics, this happens to be an important function. Okay? In fact, this is almost the normal distribution. And it turns out that if you let this go from minus infinity to infinity, you have the bell curve. That's that bell curve that everybody talks about. You know, do you curve your grades? And then I'll say, give me the equation for the bell-shaped curve, and then I'll curve my grades for you. And I'm not going to anyways, but this is almost a bell-shaped curve. The thing is, for this to be a bell-shaped curve, this has to equal a 1. And I don't think this is equal to 1. Okay? Because when x is equal to 0, y is equal to 1, then if this area is 1 and this is a bell-shaped curve, then this is probably not going to have an area of 1. So what we need is we need to multiply this by something, a constant, so that this can be equal to 1. Right? What constant do we multiply by? Well, if we multiply or divide by c on both sides, then we'll figure that out. So people were interested in trying to figure out what this is equal to, so that they can figure out what c should equal to. I guess c should equal to the reciprocal of this thing. Okay? So this is the problem. We want to look for what this is actually equal to. And in Calc 2, when you dealt with integrals, you couldn't do it. And then you dealt with indefinite integrals with infinite limits, and still hard to do, but you still couldn't have done this. And so, but you can approximate it, and that's what people did. And so with tables, they came up with tables for statistics to help approximate your standard normal distribution. But with the tools that we just learned, we can do it now, it turns out. So here's how I learned it. I didn't learn this in calculus. I actually learned this while I was taking a probability class, and it was really interesting. So what they did was they're going to let this equal to some variable. I don't know what that is. So it looked like magic when I saw it the first time. So this is our magic trick for today. What we're going to do is we're going to square both sides. So I want to find out what I is equal to, and I want the reciprocal of that so that I know what to multiply this by to make this a regular probability distribution. So if I square both sides, I'll have I squared on the left, and on the right, I'm going to do something kind of weird. And I'm going to write this integral twice, but the x in the integrand is sometimes called a dummy variable. Why is it called a dummy variable? Because you can replace it with anything you want, right? I can put mu or sigma or y there, right? And that'll give me the same result. Especially because I have constant limits. Well, they're infinite, but they're still kind of constant. So remember when we have an integral and x's and y's can be separated as factors, and then we broke up to two different integrals? Well, this is kind of like what we have. Let's work backwards. We have two integrals with x's and y. Let's put it together into one double integral. So we have an integral of e to the minus x squared times e to the minus y squared dx dy and dx goes from minus infinity to infinity. And the fact that these are constants, I mean, granted they're infinite, but they're still constants. You can think about them as constants. We can switch the order of integration. One's not dependent on the other and stuff like that. So I have two things that I want you to focus on. First of all, what is your region? The xy plane, all of it, right? All of R2, the xy plane. Second of all, the E can be seen as just a negative x squared minus y squared into one exponential function. So, let's think about this. We have the infinite plane, and we have this. Now we have x squared plus y squared if we factor out the negative sign in the power. And when you see an x squared minus x squared plus y squared, what should you start gravitating towards? R squared. So like a polar coordinate thing, right? So if you have the infinite plane and you want to express this in polar coordinates, we can think about this a little bit differently now, right? Let's express the infinite plane in polar coordinates. What does R go to? From R can go from 0 to infinity. And what does theta go from? 0 to pi. So we can rewrite this in polar coordinates by going to a double integral of e to the negative r squared. X squared plus y squared becomes r squared. And then the dx dy becomes what? R dr d theta. So the dr goes from 0 to infinity. The d theta goes from 0 to 2 pi. Okay? Now, is this so impossible anymore? So it looks like we can take it apart again, right? So let us imagine that we're going to, one part of this is going to be the integral from 0 to 2 pi of d theta, which is just going to be theta, which is just going to be 2 pi. But I'm more concerned about doing this integral. So this integral, because you have to do the appropriate thing with improper integrals, it would be an integral from 0 to b of e to the minus r squared r dr. And then so you would integrate this by u substitution. U is equal to negative r squared, du is equal to negative 2 r dr. So the r dr gets replaced, and then the negative 2 goes out, or negative 1/2. So we have the integral of e to the u du, and this is going to be just negative 1/2 e to the u, and u is equal to negative r squared from 0 to b when we put in the limits. So if we put b in there, we're going to get negative 1/2 e to the negative b squared, and if we put 0 in there, we just get 1/2, right? It turns out that as b goes off to infinity, this whole thing goes to 0. So this is all you have, negative 1/2, or negative negative. Make that a positive 1/2. Okay? Oh, and then you have the 2 pi. So your integral then becomes the integral from 0 to 2 pi d theta times the 1/2 that we just got. So that's 2 pi times 1/2. So that's pi. So I squared is pi. So I is equal to the square root of pi. Okay? So that means this integral from minus infinity to infinity of e to the minus x squared dx is actually equal to square root of pi, right? So if we want this to be equal to 1, we have our standard normal distribution, 1 over square root of pi, integral from minus infinity to infinity, e to the minus x squared dx. Okay? So that was one of the big achievements in math in trying to establish the standard normal distribution. And it's based on trying to do this, if you want to do this by hand, it's based on knowing information about double integrals and polar coordinates. Okay? Your last problem in polar coordinate section has something to do with this. All right, I think that's it.